Last day of Unit 1. So it's a good thing because then you're going to have quite a few days. Our test is not until Friday, so you have plenty of time to prepare for it. Starting out, we are going to figure out what a limiting reactant is and then learn about percent yield. Those are the two goals of the day. So let's start with this problem. This problem says determine the moles of CO2 and H2O formed when 2 moles of ethane react with 10 moles of oxygen. So I'm looking for moles of each of these guys when I start with 2 moles of this ethane and 10 moles of oxygen. How does this look different than the problems we did last week that were just plain old stoichiometry? Pierce. One of them's not. One of them is what we call the limiting reagent. But more basic, how do you recognize the fact you need to figure out which is the limiting reagent, Grant? Exactly. You've got 2 pieces of information here rather than 1 piece of information. Before, all you had to do was take the one reactant you were given, because we assumed the other was an excess. Remember, I put a big X through the other one, and stoich over from that one. In this case, oh well, we have 2 to choose from, so we have to figure out which one's the limiting reactant. I do LR for short, and so the first step in determining the limiting reactant is always find moles first. This problem is very, very nice because they gave us the answer. They gave us, our reactants in moles. Okay, so I kind of do a little chart. I'm a big chart person. And this is it. So we start out with 2 moles of this and 10 moles of this. Now the next thing we have to do, and I'll tell you why in a second, is divide by the coefficient in the balanced equation. We can't assume just because there's less ethane, it's going to run out first. Why is that? They use it up at different rates, meaning for every 2 of those, 7 of those are used up all at the same time. So looking at moles alone won't help. We've got to look at how many moles of each we need to complete the reaction. So I'm going to divide this one by that coefficient of 2, and I'm going to divide this one by the coefficient of 7, and I get a 1 here. And what's 10 divided by 7? So 14.2-ish. We don't really need to know that exactly. What's important is knowing that this number is smaller than that number. We're never going to use these numbers that I've written down for anything else. It's only to figure out which one's going to run out first. So since this one is smaller, this is going to be our limiting reactant, and this one is an excess. That's going to run. That's going to be, we have plenty of it. So now we know that we're going to do stoichiometry from here to there to find carbon dioxide. And to find water, we could either go from here to water, or we could go from carbon dioxide to water once we know the carbon dioxide. Remember, stoichiometry, you can go anywhere you want. So let's go ahead and start. And these numbers, guys, make it so easy. This is just coincidentally super easy the way the numbers work. So because I was given moles from that ethane, I'm going to start with my 2 moles of ethane. What do you want me to find first, CO2 or H2O? CO2. So for every 2 moles of ethane, this is the balanced coefficients, I have 4 moles of CO2. So, if you pull your calculators out, I might look at you funny. So we get 4.00 moles of CO2 is produced. Okay? And then we can do the same thing for water. Start out with my 2.00 moles of ethane. For every 6 moles of H2O, I have 2 moles of C2H6. And this is a coincidence in the problem that we're getting the same number of moles as the coefficient. That is not always the case. So please don't get used to that. Moles of, whoa, what am I on? H2O. Okay, how do you feel about that? Pretty good? Now I'm going to kind of add on to this question and I'm going to want you to tell me how many moles of oxygen do I have in excess? Does anyone have any idea how we can do that? How many moles are left over? Because we're not using it all. Nice. Larson says stoic from C2H6 to oxygen. What does that give me? Not the number. What does that mean? The number used, correct? So how do I then find what's left over? Good. Subtract from the original. You guys are on it. So 2.00 moles of ethane. I'm going to go straight to oxygen. So for every 2 moles, I have 7 moles of oxygen. So that gives me 7 moles used. How many in excess then? 3, because I start out with 10 moles minus 7. 3 moles in excess. Now, the way I just taught you limiting reagent may be different than the way you have learned it. If you learned it a different way and prefer to do it a different way, I'm okay with that. I only choose this method because I really feel that it's the fastest. All right? Now, any questions on this? Okay, let's do one that's a little bit more challenging, or it's not so pretty. Calculate the mass of calcium nitride formed when 50 grams of each react with each other. So we have 50 grams of calcium reacting with 50.0 grams of nitrogen. Okay, how do I know this is a limiting reactant problem? I've got information about both reactants, and I need to figure which one is going to be the limiting reactant. So, what's my first step in all my limiting reactant problems? Convert to moles. So we're going to find moles first. So I'm going to have 50.0 grams of calcium, and the molar mass of calcium is 40.08. I'm going to find moles of calcium, and my nitrogen, I have 50 grams divided by 28.02 grams per mole. So how many moles of calcium do I have? 1.25. And how many moles of nitrogen do I have? Y'all are on it today. It's much better than on Friday. Or not Friday, Thursday. Okay, so that's how many moles I have. At this point, I still don't know the limiting reagent because I have to look at how much of each is required in each reaction, and it's a 3-to-1. So I need to divide each by the coefficient, and for every 3 of those, 1 of those react. So what's 1.25 divided by 3? 4.17, and this is 1.78. 0.417. Yeah, I was thinking, oh, that's big. 0.417 and 1.78. So now we can see which one's smaller. Which one's going to run out first? Calcium is my limiting reagent. This one's in excess. All right, so we can do, bam, stoichiometry from there forward. And so I'm going to start down here since I have the whole bottom of the screen. 50.0 grams of calcium. Oh, you know what I can do? Why do that again? What do I have? I already have the moles right here, and I'm just going to use those. Why do this work twice? Right? So 1.25 moles of calcium. Okay, I'm going to stoich over for every, what's my stoichiometric ratio? For every 3 moles of calcium, I have 1 mole of calcium nitride. And then for every 1 mole of calcium nitride, I have 148.26 grams of calcium nitride. 61.8 grams of calcium nitride. Awesome. Okay, and someone just tell me in words, if I wanted to figure out how many grams of nitrogen are in excess, what I would do. Okay, where am I going to start, Morgan? Start with calcium and stoic over to get the grams of nitrogen, and then subtract from the original 50 to figure out how much is left over. All right, muy bueno. Y'all have this stuff down so far. Okay, ready to move on? We're going to add something new, and it's not really new. I think all of you did this in your Chem 1 classes. Just a little reminder what this is about. This is called percent yield. And what percent yield basically is the measurement of how well an experiment went based on what an experimenter got in the lab compared to what they theoretically should have gotten. Percent yield, percent recovery is kind of the same thing. So the formula for percent yield, and you just need to learn it, it's not that hard, is actual yield over theoretical yield. I just do A over T. That's how I remember it. A comes first in the alphabet. It's over T times 100. Now what is actual and theoretical? Actual yield is the yield the experimenter got in the lab. Sometimes you might see the word actually. Sometimes they'll say in the experiment or experimental yield. That's all the same thing. You might see experimental. This number has to be given to you just straight up. Take it. You got to be given. Theoretical is in a perfect world, in a perfect scenario, how much theoretically should have been produced. So to do that, you actually have to do stoic. Theoretical yields have to be calculated. So actual over theoretical times 100. The way I bring this to kind of normal stuff is, say you had a 100-point quiz, and you actually got an 85 of it on it. What is the theoretical grade in a perfect world? 100. So to find your percent, don't you do 85 over 100 times 100? That's exactly what's going on here. Except this theoretical is not always 100. Okay? All right, so let's take a look at this example. It's kind of a cool example. It says methanol, also called methyl alcohol, is the simplest alcohol. It's used as a fuel in race cars, and it's a potential replacement for gasoline. Methanol can be manufactured, now this is, we're going to write an equation from this, by combining carbon monoxide, what's the formula for that? Plus hydrogen. And we're going to make methanol. They gave us the formula. What's the formula for methanol? OH. Now, before we go on with an equation, what do we always have to do? Balance it. So what do we need to do to balance this? Yeah, if we put a 2 in front of the H, that balance, I think that takes care of us. Okay? So now we can look at this balanced equation and apply whatever information they're giving us. Suppose 68.5 kilograms of CO. 68.5 kilograms. How many grams is that? 68,500 grams of CO is mixed or reacted with 8.60 kilograms of hydrogen. So that's 8,600 grams of hydrogen. Calculate the theoretical yield. What is theoretical again? I have to do stoic. So I'm going to do stoichiometry to figure out how many grams of this are produced. Oi, where do I do stoichiometry from? I don't know. I got to find the limiting reagent. Gosh, more work. All right. So looking at this, I'm going to convert carbon monoxide to moles, 68,500 divided by the molar mass of 28.01, and hydrogen, 8,600 divided by 2.02 grams per mole. And then how many moles do I get of each of these guys? Louder, I'm sorry, Grant. 24 point or 2445? 2445. 2445 and 4257. 2446? Okay. That's close enough. All right. So now we've got our moles of each of those, but I can't just be like, oh, CO's smaller. What do I have to realize? I've got a 1 to 2 thing going on here. For every 2 of those, 1 of those is used up. So I got to divide this by 1 and that by 2. So we get 2,445 here, or 6. And how many moles here? Ah, that changed things, didn't it? So now which one's going to run out first? The hydrogen. We're not going to use any number again except for this one. This is our moles. We can use this number again. This is an excess. Don't care about the carbon monoxide. Even though in the real world we kind of do care about carbon monoxide because it's kind of deadly. Here. Go to there. So we're going to start with our moles, 4,257. I could have started with grams. So if you did that and you set it up with 8,600 grams, that's fine. I'm just trying to cut out an additional step. So for every 2 moles of H2, I have 1 mole of CH3OH. Got to get to grams. So for every 1 mole of CH3OH, my molar mass is 32.05 grams of CH3OH. And what do we get for our grams? Our theoretical yield. 22? I feel like I'm in a room of a bunch of people speaking a language I don't understand. 68 to 20 grams. Okay, I think that I was thinking it was four digits. That's why I was really confused. Okay, 68,220 grams. That's our theoretical yield. So that was the answer to the first part. Calculate the theoretical yield. There it is. Now it says if 3.57 times 10 to the 4th grams of methanol is actually produced, they're being really nice here, guys. You're not always going to be given the word actually. Just be aware of that. If they just say if is produced, you know, you should be able to do this without that word. Okay. What is the percent yield? So what do we do now? What do I put on top? 3.57, the actual yield, divided by the theoretical yield, which I just figured out, 68,220. Give me 3 sig figs in my final percent to stick with this. 52.3%. Not super efficient, huh? There's a lot of reasons we could lose percentage in a situation like that. All right, are you good? Good in the hood? Only 2 more problems for the unit. It's very exciting. All right, next. A common laboratory method for the determination of arsenic is described in the reaction. Oh goodness, we have 3 reactants this time. If 2.50 grams of arsenic, of AS2O3, is mixed with 4.50 grams of I2 and 4 grams of water, and the reaction proceeds to completion, which reactant is the limiting reactant? Oh gosh, so what's the first step of what I need to do? Convert them all to moles. Got to do that first. So I have AS2O3 being 2.50, and I have I2 being 4.50, and I have H2O being 4.00. All their molar masses, AS2O3 is 197.84 grams per mole. This is 253.8 grams per mole, that iodine, and then water is 18.02. All right, how many moles of AS2O3? 1, 2, 6. All right, I2? .217. 0.2017. 0.017, and then water. Oh, I like that number. Okay, there's our moles, but now we got to take into account that mole ratio, right? So we're going to divide this by 1 and by 2 and by 2 in order to figure out what's going to run out first. This one I can do without a calculator. Woohoo! I can do this one without a calculator. And that one's about 0.008 something. What is it? 85-ish. All right. So I could have just looked at that as being 0.008 something and know it was the smallest. All right. So this one is going to run out first, and there's our moles. These two then are in excess. So that's the answer. The limiting reagent or reactant is iodine. Okay? Calculate the mass of As2O5, which is theoretically possible. So now what am I going to do? Stoic. We're looking for the grams of this from iodine, because that was our limiting reactant, and the rest were in excess. So I'm going to start with my moles. You okay with that? 0.017? Yes? Okay. Okay. Oh, it's moles of iodine. Thank you. Brain fart. Moles of I2. For every 2 moles of I2, I have 1 mole of As2O5. And then I got to get to grams. So for every 1 mole of As2O5, I have a molar mass of 229.84 grams. And to go ahead and give me 3 sig figs from this. 1.95, thank you. 1.95 grams of As2O5. All right, so we answered the theoretical yield question. Okay, I'm going to move this up. If only 1.80 grams is actually produced, again, you'd have to be able to answer it without that word actually. If only 1.80 grams is produced, determine the percent yield. Percent yield is actual over theoretical times 100. What's my actual yield? What's my actual yield? 1.80 grams. What's my theoretical yield? And then how did this lab guy do? 92.3%. Not too bad. That's actually really good for in-lab percent yield. Okay, so those are all the examples I'm going to do about that. This next problem has a little bit different twist to it, but is everyone good with limiting reagents up to this point in percent yield? Okay, this next problem is a combustion analysis problem that was on the homework a while back, and I said, oh, we're going to do it. Try not to stress out about it. Do y'all remember what I'm talking about? It was a problem I told you guys to skip, and you'll be able to do it later. This is a super important triple. This is on the test. I'm just telling you right now. So we call it combustion analysis because we're going to be using the products of a combustion reaction to find stuff out about our reactant. So our reactant here is naphthalene. And this naphthalene is a compound containing only carbon and hydrogen. So all we know about naphthalene is it has carbon and hydrogen in it. Determine the empirical, it says, and it was burned in excess oxygen to give, what is the combustion of any hydrocarbons products? CO2 and H2O. And this problem says, hey, it was burned and it gave 0.0103 grams of this. Not to mention that we started out combusting 0.00300 grams of this. Determine the empirical formula and then the molecular formula. So we don't know these, right? So because we don't know those, can we balance the equation? No. Okay. So we have to figure out what we're going to do, and that's based on what we call the combustion analysis. All right. So I'm going to ask a general question forget about this for a second. In general, if I were to give you a compound of 2 different elements and say, I need you to find the empirical formula of those elements, what would you need to know about those elements? No. If you're doing an empirical formula problem, that's just nomenclature. Moles, what if they don't give me moles? Grams. We at minimum need grams, right? So if I have 2 elements and I know they're grams, I can convert them to moles, and then what do I do in an empirical formula? Divide by the smallest moles to find the whole number ratio, right? So I need grams of what in this case? Carbon and hydrogen. If I have grams of carbon and hydrogen, I can then find the empirical formula of carbon and hydrogen together in this scenario. Are we good with that? Okay. Now, notice that they give me the grams of CO2. I'm going to say this, law of conservation of mass. What does that mean with what they gave us? They said we have 0.0103 grams of CO2 produced. What is that telling us, Grant? Okay. Yeah, you're getting way far in advance. In general, what is that? You're on the right track. But I want it simply stated, what do we know about that carbon dioxide compared to the original compound? Okay. Well, no. Okay, take away the minus part. Same amount of carbon. That's what I'm trying to get you to see. Do we not agree that this is the only product that produced carbon, that carbon's in, right? So due to the conservation of mass, all the carbon here came from where? Here. So all the carbon in that CO2 is the same amount of the carbon that's in our original. Okay? Because we can't do stoichiometry here because we don't know anything, we just need to figure out how many grams of carbon are in CO2. That's all we need to figure out. So we're going to take our original amount of CO2, and I want to get within, this is an internal little analysis of just that CO2. How do I get to grams of carbon in just CO2? Molar mass of carbon? Carbon dioxide. So for every 1 mole of CO2, I have 44.01 grams of carbon dioxide. Okay, again, I want to get to grams of carbon. Now where do I go? For every 1 mole of CO2, I have 1 mole of carbon. And now, for every 12.01 grams of carbon. All right, so give me a lot of, just don't be afraid of the sig figs here. How many grams of carbon do I have in this equation? Two grams? It's times 10 to the something. All right, grams of carbon. That's how many grams of carbon are in that carbon dioxide, which means that's how many grams of carbon are in my compound. All right, now we need grams of hydrogen. But they didn't tell me how much water. If they would have given me water, I could have done the same thing with the H, right? But they didn't tell me that, so I have to figure it out another way. Subtract, exactly. Remember, the only thing in our compound, in our 0.003 grams, is carbon and hydrogen. So by subtracting the amount of carbon we just figured out, we can get grams of hydrogen. So, what is it? Give me a couple more sig figs. Really? Okay. Times 10 to the negative 4th grams of hydrogen. Now, why isn't it grams of H2? Isn't H a diatomic? Good. That's because H is not by itself there. H is in the compound with carbon, so it's not a diatomic. All right, now I have my grams of both. I can now go set up my little empirical formula table that I always like to do. So it's 0.00281 grams of this and 1.90 times 10 to the negative fourth grams of that. Divide by the molar masses, 12.01 grams per mole and 1.01 grams per mole. All right, so carry it out for me. How many moles of carbon do we have? Nice and loud. Times 10 to the negative. All right, and hydrogen? .881 times 10 to the negative 4? Yes? Yep. All right, so those are my moles. How was it now that I find the mole ratio? Divide by the smaller to find the lowest whole number ratio. So I'm going to divide each of these by 1.88 times 10 to the negative 4. 1.88 times 10 to the negative 4. So for C and H, I get, this is a 1. .245, right? Right in there? All right. So right now my answer is C, 1.25, H1. Could that be the answer? Nope. So what do I multiply by? By 4. So I get C, C5H4. So we're saying that's my empirical formula. All right. Then it says the formula weight of naphthalene is 128. So they're saying the molar mass is 128. So how do I find the molecular formula? Find the molar mass of the empirical formula. What does that come out to be? About. You don't need like 2 decimal places. 64. Huh. What can you tell me about that relationship? It's double, right? So what would this be if this were double? C10H8. And that is the molar mass, the molecular formula, excuse me, of naphthalene. My first day of high school, this is the right answer. So, okay, question. The 64 came from the molar mass of your molecular formula, empirical formula, 5 times 12 plus 4. All right, so my first day of going into Chem 2, I remember this very clearly. There was this thing on the board, and it was a little monster. And he had scary, hold on, that is not a right diagram. Scary looking eyes. And he looked like this. He was all hairy. And then he had a little bubble coming out of his mouth that said, "I hate moths." And I was like, what is that? And she wouldn't tell us, and she wouldn't tell us. And finally we got to doing problems like this and did some organic. And it turns out that naphthalene, this stuff here, is really mothballs. Have you all ever smelled mothballs? They're kind of not as popular as they were back in the day. Lots of grandmas used them in their chests and their like hope chests and things like that to keep moths away. But because of this, I've always remembered what naphthalene looks like. And you're going to learn later in organic how the structure works. But at each intersection of lines, that's 1 carbon. So if you go around and count 1, 2, 3, 4, 5, 6, 7, 8, 9, there are 10 carbons in this ring. And then each is filled with hydrogens until everything gets 4 bonds. And the circles mean double bonds are alternating throughout the structure. But anyway, now you know what naphthalene looks like. And that is the formula for naphthalene, C10H8. All right, I think that's it for the unit. 1 unit down. We're only doing 13 to go. Last year we did 15, but they got rid of a lot of stuff on the AP, so we're not doing a separate organic unit. So you guys get to learn more organic next year if you take organic than you do this year. All right, that is all. Start on your homework. You can go back now and check it if you had trouble with last night's homework.